Welcome to The Explainer. Today, we're going to break down one of the most fundamental concepts in all of biology, the ecosystem.
Now, you might be thinking that that's a bit of a weird question, right? But stick with me, because the answer is actually fascinating. It reveals this incredibly elegant logic that connects all life on our planet.
See, the thing is, both of them, the tiny fishbowl and our whole planet, are examples of an ecosystem. And really, an ecosystem is the foundational, functional unit of nature. It's the stage where the whole drama of life plays out. So here's the key takeaway. An ecosystem isn't just about the living stuff, what scientists call the biotic components. It's also about how they interact with all the non-living or abiotic things around them. We're talking water, soil, sunlight, you name it. It's this incredibly complex web where everything, and I mean everything, is connected.
And you'll find these systems at literally every scale you can imagine. So, to get a handle on it all, ecologists have broken them down into a few broad categories.
Okay, first up, we can just separate them by location. You've got your terrestrial ecosystems on land, and of course your aquatic ecosystems in the water. Simple enough, right? So, another way to look at it is by their origin. Some are completely natural, like a huge forest, but others are actually created and maintained by us humans. We call these anthropogenic ecosystems. A perfect example is a farmer's crop field, or, that fishbowl we were talking about at the beginning.
Okay, so how do all these different systems actually work? Well, it turns out they all run on the same basic engine. And this engine has two and only two core functions: productivity and decomposition.
A great way to think about it is like a totally self-sustaining city. Every city needs a power plant to bring in energy, right? That's its input. And in an ecosystem, that's productivity. And it also needs a super efficient recycling department to handle all the waste. That's its output, and that's decomposition.
So when we measure this energy input, we look at it in two ways. First, you've got gross primary productivity, GPP for short. That's the total amount of energy that plants capture. Think of it like a gross salary. But, just like us, plants have to pay their bills. They have living expenses. They use up some of that energy just to live, a process called respiration. So what's left over? That's the net primary productivity, or NPP. And that is the take-home pay that becomes available for the rest of the food chain to eat.
Now, on the output side, that recycling process, decomposition, it's an absolute masterpiece of natural engineering. It all happens in 5 key stages, methodically turning all that dead material, or detritus, back into the raw building blocks for brand new life.
And get this, the scale of this natural engine is just, it's mind-boggling. If you add up all the net productivity, that take-home pay we talked about, on the entire planet for just 1 year, it comes out to a staggering 170 billion tons of organic matter. Just try to wrap your head around that.
But here's where it gets really interesting. How does that massive number break down? You'd probably assume the oceans do most of the heavy lifting, right? They cover 70% of the planet. But the data tells a completely different and pretty surprising story. The oceans only produce about 55 billion tons. Meanwhile, land, which is only 30% of the surface, cranks out an incredible 115 billion tons. That's more than double the oceans.
So what's the deal? Why is the huge ocean so much less productive? Well, it really boils down to two main things. First, sunlight, the fuel for the whole process, just can't get very deep into the ocean. And second, some of those really crucial nutrients, like nitrogen, are way less available in seawater than they are in the rich soil we find on land.
All right, so we've got all this energy being produced. But the big question is, how does it actually move through an ecosystem? Well, that is governed by a fundamental law, the flow of energy.
Okay, it all kicks off with the producers. Let's imagine a plant captures, say, 10,000 units of energy from the sun. This is the very bottom, the base of the food chain, what scientists call the first trophic level, which basically just means feeding level.
Okay, now along comes a primary consumer, let's say a grasshopper, and it eats that plant. But here's the thing, it doesn't get all 10,000 units of energy, not even close. A huge amount is just lost as heat while the grasshopper goes about its day. In the end, it only gets to store about 1,000 of those original units.
And you can probably guess what happens next. The pattern just keeps going up the food chain. When a secondary consumer, like a frog, eats that grasshopper, it gets an even tinier fraction. We're talking just 100 units of that original 10,000.
This brings us to a really crucial concept, the 10% rule.
On average, only about 10% of the energy from one trophic level actually makes it to the next. And this one simple rule explains so much, like why food chains are rarely super long. There just isn't enough energy left to support a lot of levels.
So this 10% rule gives every ecosystem a very specific, very predictable structure. And the best way to visualize it is with something called ecological pyramids.
Now, we can build these pyramids in 3 different ways. We can do it by number, just counting every single organism. We can do it by biomass, which is basically the total weight of all the living stuff. Or we can do it by energy, tracking that flow we just talked about.
And because you lose so much energy and mass at each step, most of these pyramids are upright, wide at the bottom and skinny at the top. Take a grassland, for instance. You could have nearly 6 million plants at the base, all of that just to support maybe 3 top carnivores at the very peak. It's wild.
But of course, nature loves to throw a curveball. The pyramid of biomass can sometimes be inverted, flipped upside down. So how is that even possible? Well, in an aquatic ecosystem, the producers are these tiny things called phytoplankton, and they reproduce and get eaten so incredibly fast that at any one moment, their total weight is actually less than the weight of the zooplankton that are eating them.
But, and this is a big but, there is one pyramid that can never, ever be inverted, and that is the pyramid of energy. This isn't just a biological tendency, it's a fundamental law of physics, of thermodynamics. Energy can only flow in one direction, and you're always going to lose a bunch of it as heat along the way. It's a rule that nature simply cannot break.
And that brings us right back to where we started, that deep connection between the living and the non-living. The total amount of life in an ecosystem, what we call the standing crop, is completely dependent on the amount of non-living nutrients in the soil or water, the standing state. It's this perfect, beautiful, continuous cycle. So the next time you see a pond or walk through a forest, maybe you'll see it a little differently. You'll see that invisible engine at work, the blueprint of nature itself, showing us how everything is truly connected.